Let me start off with a joke. This is an emergency response joke. It might not sound like it, but technically it is. So, oh, is it time? Okay, so in one of my former careers, I worked for the FIRMAC, the Federal Radiological Monitoring and Assessment Center. They're the federal emergency responders for radiological events. And about 10 years ago, NASA was launching this rocket off to Pluto that had this huge radioisotopic thermoelectric generator on it. And so in order to do that, it was like 200 curies of plutonium. 238 was on this thing. And so in order to do that, they had to pre-deploy all of the emergency response assets. Well, I was one of them, so I had to pre-deploy. That way, if the thing goes off on the pad, you know, you can characterize it, you can assess it, you can issue all the recommendations, you can control it, you can do all of the emergency response actions just like that, virtually instantaneously. And so in the process of pre-deploying, we had to get onto the base. Cape Canaveral, it's an Air Force base. And so the way that they did it at the time was they took a little photo of you, and that would go on your badge, and then you had to sign your name with a stylus, and then that would go on your badge, so you'd know your signature. So your signature would go on your badge. And so after I got my photo taken, I went over to the station to put my signature on there so that would go on my badge. And remember, this is Cape Canaveral. I went to do that, and I stopped. The thing was covered with ballpoint pen, just scribble. But then I looked at it, and I realized it wasn't scribble, it was signatures. So I looked to the lady behind the desk. I kid you not, I quote, I said, "You've got to keep ballpoint pens away from this thing. It is covered with signatures." And the lady, I quote, she said back to me, "I know, we get a lot of rocket scientists through here." That really happened. It's the green, yeah, okay.
Okay, good afternoon, everybody. Welcome to SIREN. My name is Sonja Schmid. I'm a faculty member in the Department of Science, Technology, and Society at Virginia Tech, and I co-direct the graduate program in Science and Technology Studies here in Northern Virginia. This is the 21st event in this series of seminars, talks, and discussion on nuclear emergency response. The series is part of my NSF Career Award on globalizing nuclear emergency response, and in the spirit of this type of grant, we emphasize the importance of both research and education in the area of nuclear emergency preparedness and response. So all SIREN speakers are meeting with graduate students as part of their engagement, and we plan to provide access to a recording of their lectures. SIREN stands for the Seminar on Interdisciplinary Research and Education in Nuclear Emergency Response, and it's generously supported by Virginia Tech's Office of the Vice President for the National Capital Region. Many thanks to the staff of the Virginia Tech Research Center's Briefing Center and the IT team for their support, and to the students, staff, and faculty in the Department of STS for helping to make this happen. Today's talk will be live streamed, and last time I checked, we had over 60 remote participants signed up. These attendees are joining us not only from our main campus in Blacksburg, other U.S. universities, federal agencies, and national labs, but also from abroad. Welcome. If you're watching us online and would like to submit a question to the speaker, please send an email indicating your name and affiliation to siren@vt.edu. Also, if you'd like to be added to our mailing list, if you're not on it already, we use it only to announce SIREN events. You can now join our Google group SIREN series. I also want to give you a short preview of the rest of the semester. On March 22nd, we'll have a team from DOE's Office of Consequence Management address training for nuclear emergency response. On April 24th, a TMI emergency responder, Lake Barrett, will share his historic experience with us. And on May 3rd, we'll have a guest from the Department of Radiation Protection, Klaus Gerke, present a German perspective on nuclear emergency response. So please stay tuned and help us spread the word. And now it is my pleasure to introduce our speaker today. Robert Hayes is Associate Professor of Nuclear Engineering at North Carolina State University. He's also a licensed professional engineer in nuclear engineering and a certified health physicist, a fellow of the American Physical Society, and has a joint faculty appointment with Oak Ridge National Laboratory through the Consortium for Non-Proliferation Enabling Capabilities. He served for many years in the Federal Radiological Monitoring and Assessment Center as an assessment scientist and as a team scientist for the Radiological Assistance Program. For over 11 years, he served as a principal engineer in the Nuclear Waste Partnership, LLC. He holds a BA in mathematics, a BS and a Master's of Science in Physics, and a PhD in nuclear engineering, all from the University of Utah. His relationship with WIPP, the Waste Isolation Pilot Plant in Carlsbad, New Mexico, goes back several years and you can fill me in on that if I don't mention everything, but from 2012 to 2016, he was a research affiliate with MIT's Laboratory for Nuclear Science and helped calibrate their dark matter telescope in the underground. He also served as an adjunct science columnist for Hobbs News Sun, the local newspaper of the city of Hobbs in New Mexico. And in 2013, he published a Kindle book compiling his best newspaper column submissions titled Nuclear Science and Technology Made Simple, So Simple. Today, he will talk about his experience as the lead of the consequence assessment for the WIPP event of 2014, where he was part of the emergency response and recovery effort which followed. Professor Hayes will also participate in a class on nuclear nonproliferation tonight, where he'll talk more about his lab's work on nuclear forensics and how that expertise is useful for safeguarding the nuclear nonproliferation regime. Please join me in welcoming Rob Hayes.
Thank you, Sonia. All right, so my shtick is to present ideas and present perspectives that you normally wouldn't have. So hopefully that's my goal. On each slide is to give you a perspective that you wouldn't have guessed was an accurate and reasonable perspective. So I'm going to be trying to do that a whole bunch here, just because that's the way I like to do it, is to look at things differently. So this is the outline of what we're going to talk about, or what I'm going to talk about, sorry. I invite questions. That would be fantastic. So I'm going to talk about WIPP. What is the WIPP? Talk about what was the WIPP before the event. Then I'll talk about what led up to the event. And then after the event, the emergency response and the consequence assessment and the recovery, and then put it all in context in terms of risk. What is the actual risk that we're looking at, and define risk and evaluate that in light of comparative nuclear events. So let's contextualize WIPP. What is WIPP? So WIPP is the world's first geological repository for transuranic waste. It's located in southeast New Mexico, and what you see here is you see these true packs. Those are the transportation packages that 55-gallon drums and other material transuranic waste will get shipped in as it gets to the WIPP site. And this is the WIPP site over here. What you see here, this big rectangular thing, this utilitarian obelisk, that just goes around the waste hoist. And you see another hoist over here and another hoist over here. This would be the air intake shaft, and that would be the salt shaft. And that's just where you have a conveyance that can go up and down. What you have down here is you have a miner. You have actually two miners. You've got this gentleman right here who's a certified miner who has a belly box, and he's controlling this continuous miner right here. It's got like a big barrel on the front of it with big teeth, and this barrel just rolls around and it just claws up, and you can see the marks on the rib over here of how this miner has cut out the salt, and that's how you mine the salt in the underground. The WIPP is actually a salt mine. It's an operational salt mine, and it was for some time before the event. So this is where it's located, and we're going to come back to this map because it will have context later on. This is where it's located in the country, in the southeast corner of New Mexico. If you blow up on that, then there's this tiny little section right here. It's basically 4 miles square. That's the WIPP site. Now, there had been a lot of nuclear activity down there. It was actually considered an energy corridor. That's where the Urenco opened up. They had the first nuclear facility license there in 20 years in the United States, where they did a uranium enrichment facility. Waste control specialist just shares a fence on the Texas side. It's a low-level waste facility where they had gone through the process to receive A, B, and C waste and other forms of waste, and they were even looking at getting greater than Class C, as WIPP was even at one point. And at one point, International Isotopes was looking at building a facility there to do deconversion. So there was just a lot of nuclear activity down in that area. So this is the political history of WIPP. It started back in 1957 when the National Academy of Sciences recognized that the most cost-effective, safe way to dispose of waste that basically lasts for hundreds of thousands of years is geological disposal. It's the safest way, the most economic way. And so it went through the process that's outlined here to eventually get approved. Now this is the technical, this is part of the technical basis for WIPP. What this is a plot from the Salt Institute, and you can see here in the Gulf of Mexico there's this huge underground salt formation right out there underneath the Gulf. But right up here, stretching from New Mexico all the way up into Kansas, and there are actually some layers that go up into the Dakotas, but this is where it's basically a mile thick. It's huge. If you compare the size of this salt deposit to Virginia, it's probably 3 times the size of it in square area. And so WIPP is in this southwest corner where it's about, the salt is about a mile thick. And so that's kind of the technical basis. If you were to look at how much water it would take to dissolve a mile thick of salt, it would basically take an ocean. And so it's geologically stable in an extreme sense in that way. So WIPP, before it opened, it had a stellar record. It was phenomenal. It had all of the best credentials that one could get. It had ISO 14001, VPP, star status, triple crown. It basically, if there was a way that you could show that you excelled in the DOE complex, WIPP was the first to do it. They were just gangbusters. I used to have a paradigm that the main products at WIPP were regulatory compliance, safety, and quality. That was it. After you did that, then you could start talking about work. But that was the main thing, and that's pretty much what most everybody did in terms of person hours that were spent there, in terms of the paperwork, regulatory compliance, quality, and so forth, before you could actually go and get the job and start doing it. You could turn on a forklift. All of that had to be in place. So it was and is a very highly regulated environment. It is a DOE site, so it's subject to all the DOE order standards and regulations. The radioactive materials license was issued by the EPA, so there are federal regulations that govern the WIPP that come from the EPA. The state of New Mexico has the hazardous waste facility license, so their RCRA permit is what that is. That's issued by the state of New Mexico. They also do their own transportation. They design their own transportation packages, so they're also regulated by the NRC for the transportation packages. Those have to get licensed to go on the road, and when those are on the road, they're subject to DOT. There's also the Mine Safety Health Administration. It is an operational mine, so it's not just OSHA, but it's also MSHA. All the MSHA rules apply. And then there are a host of other oversight groups, both from the DOE and elsewhere. So what is WIPP waste? This is a picture to put it in perspective. So the general rule is, second law of thermodynamics says entropy is always increasing. Whenever you're doing some kind of work, there is you're locally decreasing entropy, so globally you're increasing it. And anywhere we go that we do any kind of work, you'll find a trash can. There's a trash can, and wherever there is human activity, that includes in the weapons complexes when they're making nuclear bombs. There are also trash cans. And so what do you do with the trash that's in those trash cans? You send it to WIPP. And so what you see here in this picture is a punctured aerosol can. You see some wires, you see a box, and most of it's clear. The reason why most of it's clear is it's personal protective equipment. It's booties, it's gloves, it's coveralls, it's the equipment, the material that you wear, the bubble suits, the marshmallow outfits, those kinds of things are the dominant amount volume of what was in WIPP waste that was contaminated with plutonium. If you're making bombs, those things get contaminated and you got to get them thrown away, and they require geological disposal. So here's the facility configuration. So we're coming to the end of just the nuts and bolts of the site. So what we have is a surface facility up here. This is a schematic diagram with four shafts that allow for ventilation and for material to be transported in and out of the mine. And then you have these panels down here. These panels are where the waste is set. The repository is about a half a mile down, so that's about how deep these shafts are. And this top facility up here is what you had seen in the previous picture. Now this is what it actually looked like operationally. So what you see here, or you see some 55-gallon drums, you see a standard waste box that's approximately got the same footprint as 7 55-gallon drums. It just allows you to put bigger things in there. What you see over on this side is actually how the drums and the packages are laid out in the repository. These little hairs that you see on the outside, this is RH, and I'll explain that a little bit later. But these drums that you see in here basically fill in these rooms, and that's what each of these big U-shapes are. Each of these U-shapes is a room, and this whole thing makes a panel. That big ladder thing is a panel. What you see right here, this is the bottom of the waste shaft. This is where the drums come down through the waste conveyance, and they get loaded onto this transporter right there, so that they can then get moved up to these panels where they're in place like this. Now, a picture we'll show later is going to show these super sacks. When it relates to the event. These things are filled with magnesium oxide. It's just as a buffer for chemical retardation of any kind of transport over geological time, based on the performance assessment that was done by Sandia to license the WIPP site. And you can start to see up on the top here some of the infrastructure that's required to keep the mine safe. So it holds the back up. That's what the ceiling's called in a mine. It's called the back. It holds that up by putting a bunch of roof bolts in there, and we'll look at some of the physics of the geology right here. So what we have here again is another schematic. This drawing right here, I like this because it gives you an idea of the scale. You have a football field and you have part of a room. So these things are huge. These rooms are really, really big. What we have here is a cutaway of the stratigraphy. This cutaway of the stratigraphy shows you up on the surface, but it shows you here at the WIPP repository, and all of this mile thick, is different evaporites. Calcium sulfite, sylvite, mostly sodium chloride, but then there's some potassium chloride evaporates that you get from when water evaporates the minerals that were dissolved in it. So this down here on the bottom gives you the technical basis for why salt works. What happens is you put the drums in there, and then you walk away, and when you're this deep down, the massive lithostatic pressures that salt feels causes it to move. And it's not so much that that the individual grains are morphed. What happens is that the grains slide on each other. So the grains will range in size from, say, the tip of your thumb to the size of a grain of salt. And under massive pressure, they'll slide on each other, and it becomes plastic on the large macroscopic scale, so that the salt moves. Even though you're not really changing any individual crystal, they're just reorienting so that the salt then cocoons the waste and fills it in. And you can see in this drawing here that there are these lines that give you different stratigraphy, because all throughout the repository you can see the layers. Even when you're in the underground, you can see the layers in the ribs of where you've had different types of mineral formation. And one of these is called the orange marker. And that's literally where you actually get a bunch of clay inclusions that you can see that demarcation, and you know the depth in the mine when you see that orange marker bed. But the point is that these layers are able to separate. When this back comes down, they can separate, and it can cause ground control issues. In other words, issues if you don't maintain that. What you have to do is you have to put big roof bolts. The repository open like this, big roof bolts that hold this bottom layer to the top layers. It's just standard mining engineering design, but really what it is you're holding up this beam of salt by attaching it to higher up beams. So the longer you wait, the bigger the bolts have to be. The more bolts you have to have, the longer the bolts have to be. And then even you can start to put up strips of material, and you can keep the thing open indefinitely. But if you were to try to keep it open for hundreds of years, it would end up being a big metal tube that was in there to keep it open. But you can do that. You just have to have the resources to get in there and put the steel up in there to hold it together. So this is actually the remote handled waste part of it. So I guess I'm still going on the nuts and bolts. We'll get into the fun stuff here soon enough. I apologize for that. So the remote handled waste, so not only do you have the contact handled waste, which we saw, the 55-gallon drums and so forth, those have 200 MR per hour maximum contact dose rate. Remote handled is everything that has greater than 200 MR per hour contact dose rate. So it's got a lot of cesiums and strontiums, and it even has some californiums, but it's just the higher dose rate stuff. So it has to go in these shielded containers. It looks like a big old huge dumbbell on steroids, and it's a canister that would generally have 3 55-gallon drums of remote handled waste in it. And so there's a hot cell at the WIPP site that allows them to take this RH transportation container and take off those impact limiters, open up the lid, and remotely remove the canister from the transportation package and put it into a facility cask, and that's what's seen right here. It's transferred into that facility cask in the hot cell, and this facility cask has shields, movable shields. That's what these these big protrusions sticking up there. They're shields so it can open and shut these shield valves. And it allows this, this facility cast to come up and mate to these big holes in the rib so that it can push the canister through there while you have contiguous shielding, and then it'll put a borehole plug, a big concrete shield plug, and it puts that in behind it so that the thing's always shielded. So you put this remote handled waste into the ribs while you come back in this same room and fill it with the contact handled waste. So that's what the hair was on the outside of those panels. It was basically the RH canisters where they got in placed. So I think this is the last of the background for WIPP, for the technical part. So how they were going to warn future generations is that this square right here is basically all those panels that I showed you before, and this big outer ring is the 16 sections, the 4 square mile or the 4 mile by 4 mile 16 sections that outlines the Land Withdrawal Act where the WIPP facility is. And so they're going to put a bunch of berms there. Basically, the idea is borrow from the Egyptians on what's going to last for 10,000s of years to warn future generations. And the reason why I like this and why I put it up there is because one of the things that they left there was the hot cell. And I like that because the thing is you know, it's like 4 to 5 foot thick reinforced concrete walls, right? So just don't tear it down, just leave it. And it'll let people know what's down there. There's remote handled waste. We had to have that hot cell because we had to hold that waste, and that'll give you an example of why you don't want to dig here. But then there's like a storage vault there with records and all kinds of different languages. But it was intended to borrow from that kind of permanent, you know, the engineered structures that would last forever. Okay, so that's the technical part of WIPP. So now let's build up to what was taking place that eventually caused the facility shutdown. So technically, I would say, in my opinion, WIPP earned their stellar record. They actually lived, breathed, and followed through with safety first, quality, and regulatory compliance before anything else. And so, but they also were very conscious. They were very lean, which in retrospect turned out to be a part of the problem. But here's an example of some of the amazing kinds of things that they did. When I was there, the engineers designed this standard large box. Now, there are a bunch of different packages you could put down there. You could put down the 10-drum overpacks, the standard waste boxes. But this one right here was quite ingenious because it basically replaced all of the true packs with a single large box, which in the DOE complex, if you're making weapons, you're using things like drill presses and lathes and large equipment. And when the thing breaks, it's contaminated with plutonium, it has to go to WIPP. Well, if you're going to break it down into 55-gallon drums, there's a huge volume increase because you got to break it down to 55-gallon drums. But if I could take this, let's just say it's a glove box. I take this glove box and I don't have to break it down and put it in 55-gallon drums. I can just dump a bunch of stuff in the glove box and put it in a standard large box. I've substantially reduced the total volume that's going to the WIPP. And that's what it did, and it worked quite well. In the underground, before the event, there was a lot of crazy fun science that was going on. One of the ones that I helped with was the dark matter telescope from MIT, but there were a number of other things. Stanford had a double beta decay trying to see if the neutron was its own antiparticle, which would allow double beta decay if that was the case, trying to see if it was a Majorana particle or not. And then there was low dose rate experiments that were being done by the university there, the local university, because you had low background, which is why you were doing these other experiments, low background. You know, the salt doesn't have uranium and thorium. It's just got a little bit of potassium, and what minute amount of radon comes in from the air on the surface. A lot of fun science. So now I'm going to start throwing some new ideas at you. I'm looking at this in ways that most people, in my opinion, don't look at the WIPP. So I'm going to make an analogy. I'm going to point out that the most conservative estimates for Yucca Mountain are around $10 billion, but there are others out there that claim that Yucca Mountain's cost about $12 billion. The WIPP, before the event, the total had cost around $5 billion. With the event, giving a conservative overestimate, it's going to cost about $6 billion. It's open and running now. Yucca Mountain is a hole in the ground. WIPP, as we'll see here, is halfway full, halfway done, and they had a stellar record. Apples and oranges, but yeah, they're both geological repositories, and which one is really getting you the run for your money? Again, here you see the true packs, and this is where the front gate into the WIPP right there in those pictures. So carrying on that analogy, let me take it a step farther. Let me be a little bit more extreme and point out that if you take the approximately 2 million curies that had already been there, it's about half of what they were licensed for in the Land Withdrawal Act when Congress set them out to do that. If you take that and you convert that using an estimate of about 10,000 ALI being approximately what's an LD50, that's somewhere in the range of what Alexander Litvinenko had. So that if you get about that much, there's a good chance you're going to die because you just had an overdose, 10,000 ALI. And if you say that 10,000 ALI, and you say how many of those 10,000 ALIs were in the WIPP site underground, and you take that number, you say, I'm just going to be even more conservative. I'm going to say that they never fill another drum in WIPP, and that the closing costs another $5 billion or $4 billion. That's $10 billion. It just rounds off the numbers. And you say, all right, so how many ALI do we have for that $10 billion? It turns out, it works out to about, for LD50, if you, instead of looking at ALI, you look at LD50s, it's about $100 per LD50. Now, there are a lot of things that went into that. Basically, in order to get that LD50, you would have had to have taken all of the transuranic activity and put it into pills, right? You removed it from all that PPE, right? Let's say there was only, 50 millicuries in a drum, right? You're not going to get all the activity out of the drum and put it in a pill to give somebody an LD50. But the point is that this is a way of scaling it in terms of risk. How much radioactivity have we permanently removed from the biosphere, and for how much? What did it cost us? What did it take monetarily for your tax dollars to get that permanently removed? I would say that's a pretty good impressive way of looking at it. $100 per LD50 to permanently remove it from the biosphere. So again, before all this happened, they had a phenomenal record. They were actually called the crown jewel of the DOE complex. That was their motto, their mantra. That was the way. We took pride in that. We wanted to be the best, and we were on our way to be there. There had been over 10,000 shipments without a single release. That's about on the order of about 30 trips to the moon and back. Not a single detectable release came out of it. So there was about 3 million cubic feet with about 2 million curies that were in there, and that was about half of what they were allowed to do based on the Land Withdrawal Act. When it was signed into law by President Clinton, that was the maximum they could do. And so they were they were about halfway there in about a third of the time, because there was a time limit as well. And so they were doing an amazing job, in my opinion. So then one might ask, with all of that, how in the world did this happen? What is this? Oh my goodness. This, to me, was a personal nightmare. A personal nightmare. So now let's talk about how this happened. So how this happened is it started with a miscommunication, bad conduct of operations. So it turns out when the process of making nuclear weapons, which is what they were doing at Los Alamos some time ago, is you got to remove the plutonium from the spent fuel, but after you do that, it comes with it the americium. And you got to remove the americium from the plutonium, and you do that by using very concentrated nitric acid. And so the americium goes with the nitric acid, and then the plutonium is removed elsewhere. But what you're left with is this very concentrated americium in nitric acid, which when it dries up, you get this salt material that has a very large amount of nitric acid in it. Well, like any of the other national labs, it might not be any surprise to realize that, to find out that they have some of the world's best chemists there. And the time came where the M&O at Los Alamos said to a subcontractor, you have to disposition this waste. It needs to go to WIPP. This americium is transuranic, it has to go to WIPP, it has to go there. And they said, well, how do we do that? This is concentrated nitric acid. And they say, talk to the chemists, right? They know what they're talking about. They'll give you the right advice. And they did. And they went to the chemists and they said, all right, so how do we disposition this? How do we make it safe? And the chemists said the right thing. They said, you have to mix it with inorganic material. And then they gave some examples. Diatomaceous earth, clay-based kitty litter, things of that nature. Except for when they said you have to mix it with inorganic material, the subcontractor wrote you have to mix it with anorganic material. And one of the examples was kitty litter, right? Although the chemist said it was clay-based. They just said, oh, it says kitty litter, all right? Well, and it's got to be organic material, so there's only one way to interpret that, if it's got to be an organic material. So that started it. Then the big boo-boo was when Los Alamos allowed this subcontractor to violate their permit. So they had a permit from the state basically to characterize the waste. Effectively, you can neutralize it, but you can't treat it in such a way to make it reactive. And it's exactly for this reason that we issue permits. It probably would have cost about $1 million to revise the permit, but it would have saved this, right? If they would have gone through the process to revise the permit, it would have saved this issue from happening. And as a result, I believe that this made the record, the state of New Mexico made the record for the largest financial fine to the federal government for any mistake that they made. And it was for that, because Los Alamos violated their permit. It was $70 million. And the state said, we're just being nice. And I actually spoke to them, and they were so mad. They were seeing blood after the event occurred. They wanted heads to roll. They were furious that the Department of Energy would have let this happen. And at least I know in the local Carlsbad field office, they were pretty mad too. that they just had a dirty bomb go off in their mind. Basically, is effectively what the outcome was. And so because they violated their permit, the event happened. If they spent the $1 million to revise the permit, it's a lot of money, right? But the point is that pays for experts. That pays for some of the best people out there to come in and look at it and say, what does it say? Wheat-based kitty litter? Excuse me? Right, it would have been caught, right? But you get what you pay for. And so that didn't end it, right? So then after they'd gone through this process, part of what you have to do is you have to write procedures. And when they were writing these procedures to how they were going to mix this stuff in there, an industrial hygienist was asked to sign off. An industrial hygienist had to sign off on this process of mixing this kitty litter with the nitric acid. And the industrial hygienist said, yeah, I don't think that's right. I'm no chemist, but I don't think that's right. You should go talk to the chemists about this because I'm not comfortable with this. And they said, we already talked to them. They already said it's okay. They're the ones that told us to do this. And he said, I can't sign that. So they got somebody else to sign it. They said, all right, well, you're not going to sign it. This other one will. And what do you think that other one said? When they said, oh, he's not going to sign it. We need you to sign it, right? It ended up getting signed. And then the last bite at the apple that they could have had, and there were I think 3 managers that got fired because of this, that were actually pointing out, you should have caught that, you should have caught that, you should have caught that. And then the last one was when they were actually mixing it. And the operator at the glove box was mixing it, and he went to his manager and said, should that be smoking? And the manager said, everybody's looked at this, everybody's reviewed it, everybody signed it, get back to work. Okay, went back to work, put it back, sent it off to WIPP. And so there were a lot of people fired. Even DOE got hit hard because originally it was the NNSA, and it was chosen. NNSA, this is so unacceptable, now you can't do it anymore, now it's going to be EM. And this is what it looked like. So remember I told you to look at those big white lids that were on top of the drums? This is what was left of those big white lids. Effectively what it is, it's a big polyethylene sack of magnesium oxide. And you can see the sacks are all gone. It just melted the sacks. So there was a big fireball that took place on top of these drums that melted those sacks and gave you these piles. So what happened then? So right here, I was asleep. That was Valentine's Day. It was like 11:30 p.m. Valentine's Day, February 2014. And I was all coming back from a date with my wife. And then the next morning, I was drinking coffee, and they said, get out here now. I'm like, I'm not on call. They said, no, you get out here now. I'm like, well, he's on call. Nope, get out here. I'm like, all right. Because I told you that story earlier, I'm going to tell it now. So when I got out there, it turned out that they had the facility on lockdown, and they brought me in, and they said, we need you to go do consequence assessment because we had a release. And I said, no, you didn't. What do you mean you had a release? What are you talking about? They said, we measured the filter from the effluent monitoring station, and it was showing like 100,000 DPM. I said, that's a source. That's not an air filter, that's a source. You need to put the air filter on to measure that. They said, no, it was the air filter. And I said, it was contaminated. They said, no, we checked it. It wasn't contaminated. I said, well, the instrument's wrong. It took them about 10 or 15 minutes to convince me. And the reason why I bring that up is because I was there for over a year afterwards. And in all that time, even though it took them about 10 or 15 minutes to convince me that there had been a release before I would go and come up with a plume, to figure out our plan of action to characterize it. As far as I had ever seen, and I pretty much knew everybody, I was the fastest person to believe that it actually had occurred. Everybody else took longer, because the event actually took place at 11:30 p.m., and they still let people back on site. And it was some time after that before they caused a lockdown, because it was just so hard to believe that something like that would occur. That was just beyond comprehension, that somebody would send a dirty bomb. You know, friends don't send friends dirty bombs, right? You just don't. That's just not okay. But it happened. And so the event took place right here in this panel. You can see in this little, I'll show you a bigger picture here. And at the end of this panel, there was a continuous air monitor. And this is what the continuous air monitor read. So this version right down here, this is the linear scale. What I have here is the log scale. The reason why I show the log scale is because the vendor said that the saturation rate for the detector was about 2e to the 5. And you can see that's pretty much where it was. This detector went into saturation. And these teeth that you see here, it was changing filters. So because it's a salt mine, imagine trying to do quality radiological air monitoring in a salt mine. It was challenging. It was fun to figure out how to do it, but we did. And one of the ways is that we had a continuous air monitor that would change filters. And that's exactly what it did. It went through and changed all its filters. It saturated. It was like, whoop, it pegged out, changed another filter, pegged out, changed another filter, pegged out, because it was also getting filled with, it was also the differential pressure, because all of the particulate, the salt and the magnesium oxide that was in the air, and the nitric salt plugged up the filters, and so it just changed them all out until it ran out of filters. And that was the cam. And so then after this occurred, then they called me in about 5 hours later the next morning. And the funny thing is that in that, when that cam operated, once that cam hit, it was right down here, this first little step. Right, the first little step right in there, it shifted to filtration. All of the effluent air started going through HEPA filters. Well, not all of the air, but it worked exactly. That's the funny thing about this is, and I'll explain why, everything in there for their emergency response in terms of the engineered design features, it all worked exactly as it was designed. And yet there was a release, even though it worked exactly as it was designed, and nobody had expected that until after the fact, and we realized, oh my goodness, the reason why there was a release is because it worked exactly as it was designed. Imagine that. And here's why that was the case, how that got missed. This was designed, if you look back at that timeline that I showed you, the building started back in 1985. That was before ALARA even existed. That was back when and to put it more in context, it was built to the safety specifications for MSHA. It's a mine. And so the way that you do air control in a mine is the same way that you do electrical control in a circuit, with electrical engineering, is you put up big resistors. And by having big resistors in different places, you change the airflow. And that's how you control airflow in a mine. And so if you want to have the smallest airflow possible, you have the biggest resistor possible. And that's how you get the lowest flow possible, is the resistor. That's the only way that you can control it, is with a resistor or a damper. And so these bypass dampers right here were the ones that would shut. So normally the air would come up through these filters, but when you do a shift to filtration, or it's through these fans here, these blue lines are the regular fans with no filtration, but when you do shift to filtration, so the air would come through these HEPA filters, you block off those regular 700 fans, and the air is supposed to all go through those HEPA filters. But the problem was that those dampers only met the MSHA specifications. In other words, they open and then they shut. And so how do you get zero flow through a huge damper? You don't. In fact, there was a known leak rate. It's just an extremely small leak rate. And it turns out, if you look at the activity on the effluent before the HEPA filters and after the HEPA filters, the ratio of that activity was the actual leak rate that was specified in the design of those dampers. And so exactly what was supposed to leak through the dampers did leak through the dampers, and that was the entire release, effectively. It's just that because it never went through a modification. If it had gone through any kind of a modification, it would have had to go through a whole review process again. And then ALARA would have come in. Then radiation safety would have come in. All those new review requirements would have been done. But it was in a grandfather clause. It met the requirements when it was built. You didn't have to go back and redo anything because there wasn't any modifications. And so it never got caught because of that fact that there was never a change to drive a new review. So After I was convinced there was a release, I went over to my workstation, I pulled up NARAC Web, and I made this plume. And from this plume, this drove basically the next week. And this plume, I basically said, all right, so I know what my effluent was because I have this was a fully compliant radiological monitoring program. All the air monitoring met all of the specifications for all of those drivers. And so this was a Category 2 nuclear facility with basically state-of-the-art radiological instrumentation that was there monitoring the entire thing to the extent that I knew what went up the stack fairly well, with some exceptions. And so when I went and did this plume, I ran my procedure. My procedure said, all right, so right there's this little hook there. There's this air sampler. This air sampler was located right there. So you can see this guy right here. He was actually one of the Hell Physics techs on my RAP team. We went out, we surveyed our way in. When we surveyed our way up there, didn't see anything, went up to the air monitoring station, pulled the filter, frisked it, and it was about 300 dpm alpha, which is typical for radon progeny. The values you would normally get, gross alpha for a fresh filter, would range from about 200 to 2,000 depending on the time of the day, how much radon you had in the air, radon and thoron. And we frisked it, and we went through our procedure, we brought it back, and it went through its normal assay process. And so that's what happened that morning, the day after Valentine's Day. So right here, and I'm going to jab in a bunch of hard lessons. I had mentioned before to some of these people that I had said some things in technical speak that I said before certain senior managers that didn't interpret it properly. Basically, after I brought the filter back, I said it's consistent with radon progeny. That might not sound like a bad thing, but it turned out in that case it was, because certain people thought if Rob says it's consistent with radon progeny, it's radon progeny, right? That's not what I said. I knew that there had been a release, but I knew that it was small, right? It was small enough that the radon progeny would mask it. So I didn't know if it would see anything at all, right? I don't even know if my plume was going to be right. Maybe I had the wind direction off a little bit, right? Maybe there are going to be some wake effects. Maybe there's going to be some extra lofting. This didn't account for any of that kind of thing. It was just a web-based application comparable to something like Hotspot. And so, we surveyed our way in. We weren't able to find anything that we could say this was due to the release. And that's what was reported. And apparently that was misinterpreted to say that nothing got over the fence. I was like, oh my goodness, oh wow. So that was a bad lesson, and I take responsibility for that. I've since had to learn to be careful how you talk. Even if you're saying the truth, it doesn't mean people interpret it correctly. So another big mistake that had occurred, and this was one of the M&O managers, it turns out when you look at what had occurred, if you go over the physics of this release, another assumption that was made was something that is often made in consequence assessment, and that's a puff release. Well, technically that's what the source term was, right? It was a big fireball, and you had a puff. However, that had to go through a facility, a large underground facility. And so it turns out after the fact, the actual correct model to use is the same as you get for room dilution. You assume instantaneous mixing, and then you say what's the concentration as a function of time, and it becomes, if you integrate it, it becomes a saturating exponential. In other words, it exponentially decreases with time, and then if you integrate how much is removed cumulatively, you get a saturating exponential. And so there were actually two volumes to account for, and we'll go over that later. That was another one. And then another one was that after that had occurred, I already knew that we had the various instrumentation for characterizing alpha, right? I mean, most of the waste was alpha, but it was mixed alpha and beta, and so we had instrumentation for doing that. And we knew based on testing that the instrument that the industry was promoting was this thing called the isolo. We knew that didn't work for mixed alpha and beta. And so we had to come up with our own custom algorithm. When we did that, and within a few days, we were able to show on that filter that there was around 50 dpm. Now, the uncertainties were large, but the point is that we knew, based on measuring that filter, that there was transuranic activity on that filter. This was about 3 days into it. But But what ended up happening, another lesson learned, and the DOE actually got hit for this one, and that was that they started to become tight with their information because they wanted, God and country to review everything before they released anything, so they couldn't ever say, well, we made a mistake, that was wrong. They wanted anything that they released, to be gospel truth, so that, nobody could come back and said, you said something wrong. And so the state got really mad at them for that. They said, just tell us it might be wrong and tell us what you know, because whatever you know, we need to know. And if it's got big error bars, just tell us it's got big error bars. We just need to know. You can't be holding information and not let us privy to that. And so, but that took about a month before, or at least a couple weeks before that got hammered out. So that they just started saying, all right, fine. You can see what we see, but doesn't mean you'll understand it, right? Here's the spreadsheet. here's the radioassay value for that filter number, right? Now, if you want to tie that to a given location and a given time, you got to have a lot more information, right? And if you want us to write up that story for you, you got to give us time. And so they worked it out. But that was one of the problems that had occurred, was that communication of how do you share data like that. And so we were able to overcome that. What ended up happening, one of the things why I put this on the bullets is because we knew before anybody else the level of activity that was off-site. I actually had a point I could normalize that plume, but it didn't get released, and so the credit to announcing an off-site detection actually went to the state, because they were a lot more free with it, right? They went back and they took it back to their radiochemistry facility and did measurements, and they announced it, and then after that, then we were able to announce it. It was kind of like, I don't know, kind of stole my thunder, because we did it faster, right? We were able to get a quality measurement faster, and we could have told everybody. Another one. So I was actually on the RAP team, but I was never given a RAP team. And that home team until about 5 days afterwards. And NARAC didn't even get stood up until about 5 days afterwards. I was on my own, and I was not a happy camper. In fact, there was one gentleman, and I'm not going to say his name. He actually called me up. It was like day 4. He said, hey, Rob, what's going on down there? And I knew that he was a member of a home team. I said, praise God, I've got a home team. I've got all this work. Here, help me with this. And he said, oh, I'm not calling to help you. I just want to know what's going on. And I think I saw red, and I might have even cussed, because I thought, you want me to take 30 minutes, 45 minutes to tell you what's going on, you're not going to help me. And it was the next day that an angel from God came. Her name was Rajamina, and she said, how may I help you? And I just started dumping on her so much stuff, because I tell you, when you have something like this happen, the decision makers become this information-hungry machine, this information void. They want to know everything, right? And being able to get all this information to them, get through any kind, because there actually is a process for it. You have to follow your procedure. And so being able to have help was enormous. Because it wasn't even until 2 or 3 days later that the M&O brought me other health physicists from corporate that came in to help me. Okay, so then that was the pain from that first week. After that first week, then we had a good idea what was going on. So let me give you this picture to scale things. So here's again that little corner of New Mexico. Blow up that little bit right there, and you can see this tiny little bit right here. Blow it up again here, and this is actually, when you blow that up, that little block right there, it's 4 miles on an edge, 16 sections. And that's the WIPP Land Withdrawal Act. Now, we'll come back to that a couple times, but that's kind of the scale. It's 4 miles on an edge, 16 sections. So this was the final, after all was said and done, this was the final, when NARAC got stood up and all of their fancy computers were able to do a very detailed analysis, this is the resulting plume. And we'll talk about this leg here in a little bit as well. But you can see these little flag poles, these pink flag poles. This is where air samplers were. Those ones that I went out and I retrieved those air samples, and we brought them in and we assayed them. And we're going to come back here in a little bit and compare to this contour map of the United States. This contour map of the United States came from the CDC, and that shows the cesium deposition from global fallout. And we're going to compare this to that cesium deposition from global fallout, and you'll find out that even though this looks really scary, if that's all that you saw was just this plume, you'd say, oh, that looks horrible. what I was able to find out by doing assays, by going and measuring it, is that this amount of deposition, this ground deposition, was actually comparable to, if not less than, the americium-241 that was already there from global fallout. We were able to measure it because we had a fully compliant, state-of-the-art radiological monitoring system, effluent monitoring system, the whole 9 yards. So we were able to monitor it and characterize it and assay it. But it's easy to get mixed up the difference between finding something that's easy to measure and something that's actually dangerous. Right? I mean, you can measure temperature, but unless the temperature gets up to a certain range, it's really not dangerous. Right? But it's easy to measure. That doesn't mean that it correlates with risk unless you're into a certain range. And so you can see these the 16 sections, and you can see where they do the oil drilling right up to the edge. You see those little white patches. Those are this is out in the oil patch. That's what they call this, where they were doing oil mining outside the drilling for oil outside the 4 sections. And so from these calculations on the plume, oh, that's another slide. All right, so here, this is the total activity, the integrated activity, total activity that's being released from the underground into the HEPA filters. So this is the source term, to the HEPA filters as a function of time. And what was interesting about this is that it's not a single saturating exponential. It was a superposition of 2. And what that comes from is when you look at the path, so the event took place down here in this panel, and so the air, the bulk of the air went along this path to the exhaust drift, down the exhaust drift, and then up the exhaust shaft. Now that itself would be a single saturating exponential. You assume that it's uniformly distributed throughout that volume, and then a certain fraction of it is removed continuously, and so that gives you that single saturating exponential for the total activity that's removed. But what ended up happening is this whole panel got contaminated. All these side drifts got contaminated. So when that fireball went out, it spread out. So it didn't fix itself into this one volume of the direct path out, but it expanded into a much larger volume, and it had a much lower room exchange rate. So the room exchange rate for this direct path was 1, the volume was 1, and when you looked at the actual physics, what you get is, for those 2 volumes, you use a 2-volume model, you get 2 saturating exponentials, and the data fit, it was just, I mean, look at the fit, it's a gorgeous fit. So I published it. Then the other thing I wanted to say, I mixed up the slides. When you look at these air samplers, so these aren't the only air samplers that were there. There were a number of others that were further out. So there are a number of air samplers. But when you look at those air samplers and you compare those to what was predicted based on the plume, once the plume was normalized to the effluent, because we actually had quality radiological monitoring in the effluent while the stack was coming up. And that was one of the lessons learned. The second filter, actually, one of the managers there said that they didn't want Savannah River to do a radioassay on it. It was probably the most ridiculous thing I'd heard that entire day was to find out the manager said, no, we don't care what the radioactivity is on it. We only want to know if there was beryllium or something like that. And Savannah River actually had to ask them twice, are you sure? We can measure this. We can do the isotopics. And apparently at least twice they said, are you sure you don't want us to do the isotopics? And this manager said, no, we only care about the industrial hygiene part of it. And part of that, and that's what I wanted to say here. And part of that was because of these 2 volumes, it wasn't a puff release. It was a protracted release. So that by the time we were doing this, the release was still going on. We just didn't realize it because nobody had pulled the second filter. So while we were out here surveying this, the wind had already changed and gone the other direction. So it was actually blowing in the other direction. It's not like that this was a danger. If we had been sitting there in this plume the whole time, breathing that overnight, we would have gotten about 3 millirem, which is on the order of about the dose that you get from radon from sitting from 1 day of radon. So it's a really small dose is what you would have got. Measurable, absolutely, but a very small dose in terms of total effective dose equivalent. And so even though we were here, I mean, at the time we didn't know, right? I mean, we're out there trying to characterize it, trying to figure out how bad it was, trying to assess it, doing the consequence assessment. But the plume was still going on because that second volume was still emptying because it fills such a huge volume. Remember I told you that size of that football field? It's an enormous volume down there, and it's spread out, and so both of those two volumes had to empty. And so the release went, if you look at the time interval here, it went out to, on the order of a day, many tens of hours. The bulk of it was the initial. I mean, initially, right? This is if you look at the activity in the room, it exponentially decreases, right? But that was a big lesson learned for me, is don't assume everything's a puff release unless you really know it's a puff release. And so however, this became very interesting. When you have all this quality kind of monitoring going on, when you actually have what's effectively a dirty bomb, how well can one predict the air concentration from said dirty bomb? Well, I actually plotted it. This is what was calculated from the plume, and this is what we measured empirically from these regulatory compliant air monitoring stations that were in the field. And this is a log-log plot. So this is over 5 orders of magnitude. But down here you see some over-dispersion. And what was interesting is when I published this, I was very impressed because I hadn't seen anything like this, and I'd been doing this stuff for a while. And I published this in the Health Physics Journal, and then the next month was published in a whole issue on this study that was done up in Canada where they'd done 3 dirty bombs, but it had a short half-life. And so it was a very controlled experiment where they did just crazy measurements. It was like they had a field full of air samplers and radiation monitors out there, and they really did a much more thorough job on looking at how these air transport models accurately estimate measurement values. And so they just put this thing to shame. I was very impressed with this at the time until I looked at their work, and I was very impressed with their work. But what was interesting is that they also had the same over-dispersion at the lower values. And I came up with some really cool physics out of that I'm not going to go into here because that's separate. That's just cool physics. But what was of significance is that it showed how well one can, with the modern tools, calculate, if you know your source term, what the concentrations are out in the plume. So what we had to do is we had to reclaim the mine. So in order to reclaim the mine, we had to go into the mine. So in a standard health physics practice, what you do is you assume the worst. Whatever you cannot measure, you assume the worst thing that can be there that you cannot measure is there, and then you mitigate that, because then you know you're covered. And so we started by putting battery-powered, like portable air monitors on the shaft. Actually, we started at the shaft, went up the shaft, survey up to the shaft, measured the shaft. There was even some updrafting that occurred when the filtration got shut off, and so we had a bunch of air samplers there just in case activity came up, because we didn't know what was down there, right? All we knew is what we saw at the effluent, right? And what the cam had shown. And so saw nothing there, put these air samplers on the conveyance, ran it down, took a bunch of measurements, said, all right, so now that we have these measurements, and you say, well, what's the worst it could be? Made the calculation, figured out what the worst it could be, figured out how much PPE we had to throw on these people, threw that PPE on them, put them down, had them go in, survey. When they went in a survey, did again a calculation, right? I mean, how well can you see americium when it's mixed in with salt dust, right? You just assume the worst, and you kept doing that until, oh my goodness. You kept doing that until they got all the way into the rest of the mine. So I have 5 minutes. So we'll just do the pictures. We'll just do the pictures. Pictures are good. So they had to come up with new ventilation. So this is this picture here shows you where the bypass dampers were, and these were the old filters, and this is where, or the old fans, and this is where the air comes out through the HEPA filters in here. They had to have a whole new HEPA bank. So they had to, that way they could get more filtration. They got more instrumentation. As a result, this red part here shows you where, because they didn't have access to the ground, they weren't able to put up enough steel up in there to maintain safe ground control. And so the mine started to degrade. I have my own theory as to why they let that happen. I know those guys there, they're just wicked smart, and they probably had some really smart stuff that was going on, but I don't really know for sure. I just, I hypothesize on why that made sense or why that happened, as opposed to just not being given enough resources. Because I remember one of the issues that occurred, and this was funny, is that people die from heat exhaustion, but they don't die from getting 5-rem. And so if you're going to put double PPE on a person with PAPRs, and in the underground it's 80 degrees continual, and the industrial hygienist will say, well, if you're going to have these people doing heavy work and double set of PPEs in a PAPR, if it's that temperature, they can only work 30 minutes of an hour or 15 minutes of an hour, right? Because you can't let them, it's OSHA, right? It's a heat exhaustion issue. And so how do you get enough people down there to do this kind of work when you've got to do you got a full dress in and dress out with a hotline to get them in there to do that kind of work? It's just, it's next to impossible. But they made it work, so they're actually open. So they're actually doing a full waste emplacement with full contamination controls in a very dusty salt mine. And they're making it work. And so this is a picture of what it looks like. And then this was a big surprise. So one of the last things I did when I was there is I did a calculation, because this was just crazy expensive, what it would take to recover. I mean, imagine a city got hit with a dirty bomb, what that would take. Right now you're at a Category 2 nuclear facility, and you got all these regulatory requirements and all these drivers that you still have to meet and still recover. And so I did a calculation. I said, looking at how much activity was coming out of the exhaust shaft, it eventually basically went to zero. And so it turns out that if you look at the EPA license, what was released was well below what they were licensed. You could do 10 millirem per year to the nearest resident, and they were at like 0.1% of that release. So it was well within their license. So I said, all right, well, how much could we release, right? So I did a technical basis document to look at assaying the waste shaft, dropping a high purity germanium down there and assaying it, and then looking at getting a variable motor to rev up the fan so that you could actually start to let some air out without going through the filtration, without still releasing radioactivity, because it was all fixed. And that was the way they did it. They basically washed down the walls, and then they fixed it to the ground, and then they put run-of-the-mine salt and covered it, and then they put a layer of tarp over it, and then another layer of run-of-the-mine salt. So when that run-of-the-mine salt wore down, so you could see this yellow tarp, you need to go and put more in. And it didn't get rid of all the contamination, but it fixed a lot of it. So the idea was, you could save hundreds of millions of dollars if you could go back to non-filtration, but it required this graded approach. It's a very common thing. You had to step up to it and to show that you're still well below the licensed annual release level to do that. And then all of a sudden, so one of the things New Mexico had is that New Mexico State University, they've got their own oversight group, basically, that looks at this. And the oversight group said, you could save a lot of money by recognizing, you have a license from the EPA to actually release radioactivity. Just like a hospital or a university or any other person, you have a license that says you can do 10 millirem per year, right? 10 millirem, that's about what you get roundabout in a day on average, just for living and breathing in the United States. It's on that order. But that's what they could do per year as a result of operating, and that was just a big surprise. So, and then I was going to do some comparisons in terms of because, like I had said, WIPP was basically negligible. If you look at the amount of americium from fallout, basically if you have a plutonium weapon, there's a little bit of americium in there, and so there'll be a little bit of americium that will be in the fallout. And if you look at how much was there based on the CDC, and you compare that to how much was released in the WIPP, it about doubled what was there before they built the facility. Not quite, but so in other words, it was just a trivial amount, but it terrified people. Just like this would terrify people. This is the Fukushima, and yet what's interesting about Fukushima is there's an analogy. The World Health Organization and UNSCEAR basically said, it's not going to kill anybody. What killed people was the fear, panicking. And a similar thing had happened at WIPP. A lot of people got terrified, and it was basically negligible in terms of the environmental release. Now, the underground was toast, right? High contamination, very high contamination in a lot of areas, in a dry, dusty area. And then I also wanted to point out what's happening in my discipline, health physics, in terms of the linear no threshold. If you go to the best journals that are out there and you go to the review papers, here's a good list of review papers that talk about linear no threshold, and they say when you go to measure it, it's not there. You don't get increased cancer if you're just doing twice background or even 10 times background. You've got to go substantially above background dose rates to actually start to see cancer induction. And so this is a nice little list. The exception are those that are very sensitive, children and in utero. They actually do have a measurable risk at the lower doses. And then I want to talk about what is risk and risk management, and talk about cancer. A bunch of other papers show how cancer has been around since the dinosaurs. It's just if you live long enough, you'll get it. It's a disease like flu or something, I guess. I don't know. It's supposed to be believed to be similar to viral disease caused by double-strand breaks. But DNA repairs itself, and there's a lot of study on that. With linear no threshold, it has the ability to terrify people. And that looks like that's the big effect when you look at things like cesium deposition from global fallout. If you compare that, cesium and potassium, if you look here, they're the same chemical family, potassium and cesium, but potassium is naturally radioactive. It has both a high energy beta, high energy gamma. It's got a lower isotopic fraction, potassium, if you look at the journals, that's something that Americans need more, or it's bad for you not to have a balance between your potassium and your sodium. And potassium is naturally radioactive. You get about 10 millirem per year just to stay alive with your potassium. And this terrified people. It just, I don't know if I can stress that enough, right? It killed a bunch of people in Fukushima for prematurely evacuating old folks' homes and hospitals and so forth. And you can see here in this plume where it actually does go over the 4 sections, but that's just a contour. You can pick your contour at any level you want and make it go wherever you want, but that's all it is a contour. So I just wanted to end up saying, let's not be radiophobic. Let's take risk in perspective, right? A death is a death, whether it's a death from cancer or a death from falling from a ladder. Let's take risk in perspective. And WIPP did stellar. They're back open again. They're running, and they're going to start trying to make their record again. And those are my lessons learned from my personal experience, having been there and done that.
Thank you. Okay, I'm going to pass the microphone around for questions or comments. Yes, and please introduce yourself.
Oh, I'm Jason Donovan. I'm a retired health physicist. How many barrels actually blew up?
So that's a loaded question. So only one. So when we finally got back up to the face, in order to the first pictures came from a big fishing pole. Basically, it was a rigged fishing pole where we brought a camera and dropped it around and started looking around. And we only saw one drum that clearly was violated. There were others that had scorching on it. You can't actually see the center drums for a 7-pack. You can see the outer 6 ones and then only the outer rim. So if there had been anything inside, it hadn't been seen. But when you look at where the scorching was, it was centered. It looked like it was centered right around that one drum that was photographed. So even though the first pictures were taken with the fishing pole, we actually designed and rigged and deployed a boom system to actually run a camera all the way back in every nook and cranny, not just where the fishing pole thing got. And we never found another where there was visible openings in the drum. So there was only one that was uniquely identified where we could say, yes, look at that, it's open, and there's the proof, there's the picture.
And how much activity was in that?
Oh my goodness. So the funny thing is, there's another lesson learned. Apparently it originally was listed at like 200 millicuries, and then it was like, it can't be 200 millicuries. There's more than that. You know, looking at these measurements, should have been at, oh, we used the wrong template when we did the assay. We used a plutonium template. We should have used the americium template. There was actually many curies that were in there, and so that was another one of those kind of lessons learned where the pain that goes with that had to be realized. So I think the estimate now is that it was on the order of 7 curies, and something like half of it got released. But when I had left, the estimate at the time there was at least 2 curies, because there was at least 2 curies that went into the air.
Questions? Yes.
Hi, I'm Patrick Malone. I'm a national security reporter at the Center for Public Integrity, and I was a newspaper reporter in New Mexico when this happened, so I've read some of your emails.
Oh, boy.
One of the things that was really eye-opening for me when I read through the email exchanges between the two M&O contractors and the DOE folks was really not just a breakdown in communication, but an active sort of not wanting to fess up even among each other when there were still a lot of unknowns, when people were feeling their way through the issue with the organic kitty litter that was used as an absorbent, and perhaps how reactive the waste from Los Alamos was and what the folks in Carlsbad knew about it before they went down in there. Can you talk to us a little bit about how tenuous it was, or how certain folks were at Nuclear Waste Partnership by the time that they actually made their first entry into the underground? Because I know they delayed that at times and wanted to be certain of safety. And what was sort of that goalpost to say, now we feel like we can get a look at least at the underground and start to assess this, when you were at that phase of the process?
So, I'm not sure if I can answer that very succinctly. Things started to congeal when we were able to match theory with measurement, I would say. Because, like for the first week, right, there's this prediction, right? What's the quality of that prediction? No clue. Let's go measure it, right? So we went out and measured it, but it turned out that the instrumentation that we had was insufficient to characterize it at the time because of the radon progeny, right? The radon progeny, it's got a lot of radioisotopes that are in there that behave similar to other chemical elements that if you're going to try to do radiochemistry separation, they tend to go with them, and so you don't want to measure the radon progeny, you want to measure the actinides. And so it takes on the order of about a week to do proper radiochemistry to get down to the levels that are below radon progeny, unless you're using special techniques, which I'll give you a plug. We're doing that at NC State, doing some really cool research to do exactly that, because I lived it and I know how important it is to be able to discriminate quickly, because it hurts if you can't. And so when the picture started to fit together, you got the CAM, you've got the effluent, and those are matching, then you have confidence that you understand what happened, right? You have confidence that there was on the order of 2 curies that was up. That was because before the WIPP had even opened, there were studies that were done where they took aerosol particulate of different chemical natures, and they tossed them up and they measured how much would go down. So if I had a known source term, how much makes it up to the exhaust, right? What fraction? So you could normalize that. So we had estimates on that. We had the CAM, and then we knew based on entries how those activity levels increased as you went back to the face, because we surveyed our way back in there, and the activity started increasing. By the time we got to the panel, there was a fixed air sampler at the entrance of the panel, and that thing itself had 10,000 DPM. It had a lot, and so we knew. Right, we had measured that there was a large source term, and all of the measurements now were being consistent with the theory, and then that gives you confidence in the theory, right? The theory being that you had on the order of 2 curies that was released, and if you know that you have 2 curies that are released, you know how to mitigate that, you know how to control that, you know how to protect people for that, you know how to recover from that. But unless you know what you have, then you're not really going to know how to handle it, and so. Until we got to that point, if you don't know what you have, you don't know how to respond, right? That's the whole point of consequence assessment and verification. You find out what you have so you know what to do. And so at that point, that was where we were able to start talking about writing work packages to actually go in and do the kind of work that had to happen in order to keep the mine open. Basically going in and doing more roof bolting, going in and doing ground control, going in and deploying more radiation monitors. What kind do we need and how many and where, right? Once you have that picture, then you can answer that. Will this monitor work? What kind of frequency do we need these, right? You can actually do the calculation, do it, and that was where the picture became coherent, but you had to do all of that characterization. You had to know what you had in order to know how to handle it. Please.
Hold on.
And how much was that work complicated by the poor quality of the AK that was developed at Los Alamos?
So the acceptable knowledge that they used in Los Alamos, what had ended up happening, here's a funny story. So when they got down to the waste phase, we still had no idea what had happened, right? My best theory was there was a backfall. Mining engineering said there ain't no way on God's green earth there was a backfall. That thing was solid. I'm like, well, what else happened, right? How'd the drum come? The drum, there was a release. How did it go? Was it a roof bolt? Maybe a roof bolt went through it. What happened? Nobody knew. But we knew what the activities level were as you came in. And so when they put the fishing pole up and over it, right, we could see that there was a release. But then again, now what was it? And so what they brought back were a lot of the survey materials that they had. And this was like within the first week. And so I had a portable high purity germanium. And so I had asked, I think it was a DNFSB, it was maybe a DOE officer, somebody was there that was in charge. And I said, let me do an assay with this just to look for fission products in case it was a criticality event, right? Because I don't know what happened. And so he said, yes, please do. So I did. And when I did the assay, I saw something I didn't expect. So we knew there was americium, we knew there was plutonium. I saw americium-243. And the radiochemistry hadn't identified it because they used it as a tracer. When I saw the americium-243, that was a fingerprint. It was like, somebody's got americium. Who's got americium-243? And then when I announced that at one of the war group meetings, it was right after that Los Alamos said, oh, yep, that would have to be us. But before that, obviously, they were saying, nope, not us, can't be us, can't be us. But once I gave that fingerprint, then we knew. And then it was like, all right, which ones were it? And then we started identifying which ones they were, and they were in that mix, in that general area. And the one that had breached, yep, it was the Los Alamos drum.
How did the treatment happen?
Okay, so when you mix nitrate salt with cellulose, you actually can have a chemical reaction that with heat, can actually rapidly oxidize that cellulose material, and that's where the fireball came from.
Dan Blumenthal, DOE. So you said that when they were saying the unthinkable happened, it took you 10 or 15 minutes before you got convinced, and others a lot longer. And I don't think this is the first time where people don't believe the unthinkable could have happened. So based on your experience, what do you think are some ways that people who are trying to convince someone that something unthinkable happened could message it to, convince them sooner and make them believe?
So I had actually spoke with Sonia before this. And the analogy that I gave is if you heard a big explosion and somebody said, there was a 747 that crashed in the next block over, right? Are you going to believe it before you see it, or are you going to have to see it to believe it? I mean, to me, that's what it was like. It was like, okay, I'll believe an explosion. I heard it. But a 747 right over there, I want to see this to believe it. And that's kind of for me and for everybody that I saw, that was the mode. It was like, this is in our minds, this was like the safest facility in the world. I kid you not, we actually had made the record that our recordables were below those of public libraries. Right? I mean, that was the way that we did business. It was, I mean, that's how serious we were. And to find out that one of the drums went, fireball? Right? It was unthinkable that they would have done that to us. And so I can't tell you how to overcome that, other than, for me, it was just the science. It was going through all of the possible scenarios, because you have a lot of false alarms, right? And when you have the false alarms, you just do the procedural follow-through. Wait, what does the procedure do? That's what you do, right? Well, we weren't in procedure space in my mind, because we still hadn't had a release. It was somebody else's turn, right? My turn. I wasn't on call, right? And why are you calling me here, right? You measure the source. I mean, that was the first thing I thought of, right? So I actually don't have a way other than for me, it was going to the science and saying, what do the measurements tell you?
So that was your version of seeing is believing,
Yeah.
Seeing the science.
Yeah.
I'm Chris Beatty from the DNFSB. You showed the pictures with the 7 drum packets with the magnesium oxide packages on top.
Yes, ma'am.
And those were meant to suppress fire suppression?
No.
Or what was?
Okay, so all the salt, it's water evaporites.
Okay.
So because of that, they're actually water inclusions It's brine. There's water
Right, the
inclusions
brine.
in there.
Okay.
And so that one of the prized things back before the event, one of the prized things to go and find is a bubble, right? Because under the massive lithostatic pressure, that little water inclusion is just liquid. But when you release that, you can actually get a bubble. And so they're really special to find, a salt crystal with a bubble floating around in water, right? But when the stuff's moving around, when you make the opening, you can get some of that start moving. And over tens of thousands of years, that becomes the primary vector by which this stuff can transport through the salt, right? Because it's got to be, it was licensed for 10,000 years, and Sandia had to show through their performance assessment that it would, and they did. But part of that was to buffer it so that it wouldn't go into solution. So it was a chemical buffer for the brine so that the transuranics would not go into solution and get transported by the brine.
Okay.
It was an engineered feature.
I wanted to encourage our online participants, if you want to send in a question, the email address is siren@vt.edu. I have one question from Robert Holub, a research professor at the Center for Air Resource Engineering and Science at Clarkson University. He asks, have you measured the size distribution of the plutonium aerosols escaping WIPP? If not, why not?
Small, that's a great question. So,
Small size of plutonium indicates a fire. However, at Rocky Flats, the Colorado State Health Department measured repeatedly plutonium on the last stage of an impactor. It has never been explained. Can you translate that question for the non-technical people?
I can tell you what was measured. Yeah, he's asking about the size distribution of the aerosol and whether that's consistent with the model that was presented. So what ended up happening is that while I was out there taking these air samplers, there was a manager there at WIPP that took one of the second air sample that showed that there was still a second release, that the release was continuing, right? This was an effluent. This was actually what was going into the air. And they sent it off to Savannah River. And they said, we want to know if there's beryllium in there, right? That's a valid question. It needed to be answered, right? Because some of the waste had beryllium. And so that was another regulated, it's not just the radiotoxicity that could hurt somebody, but chemical toxicity could as well. So if there was beryllium, they wanted to know about it. But this manager refused to do, I don't know, all I can say is that this person felt they knew what they needed to do, and they just said, no, we just need this, and just give me a micrograph image of all of the stuff that's on it, and give me a chemical assay. Like I said, Savannah River said, you sure you don't want isotopics? Well, we could do isotopics, it's here. And I was like, no. You sure you want us to do isotopics? It makes sense, and they're like, no. And so all that we got were pictures, high-resolution micrographs of it, but because we didn't do any kind of X-ray fluorescence, we didn't or it wasn't asked to do those kinds of things, all we got were black and white pictures. And so you see a bunch of particulate that's on there, and you're like, all right, is that salt? Is that magnesium oxide? Is that the actual nitric acid component? What is that? It's a black and white photo and a bunch of white particulate. Which is which? Nobody knew. And so the opportunity was lost, and as a result, the particle size distribution was never characterized because we couldn't discriminate on the filter which kind was which, because the type of analysis that would have been required to do that was not requested by the powers that be. I can say that now because I'm an academic. They don't pay me anymore.
Okay, I have another question from François Diaz-Morin. He's a nuclear security visiting scholar at the Center for International Security and Cooperation at Stanford, who works on the science policy interaction on the back end of the nuclear fuel cycle. His question is, I believe you did mention in your talk the truck fire that happened on February 5th, 2014. Mm-hmm. It shows that several types of accidents can happen, and actually they do happen. What could have happened worst underground on February 14th? Could a domino effect have happened between the panels? And what would have been the consequences below and above ground?
So there's a bunch of questions in there. The worst that could have happened, obviously, is people would have died. Right? That's the worst that could have happened. If somebody was down there downstream, let's say in the exhaust drift, then they would have gotten a big old huge dose. There were controls, access controls about going into the exhaust drift. And there, at the time, there was nobody in the underground because of the fire that had occurred before. And so in a mine, That's actually the most dangerous thing that can occur in a mine, because air comes from one direction and it goes another direction. And if there's poison air coming from one direction, how do you get to a place where there's not poison air? You got to know your mine ventilation, right? And so that's actually the most dangerous thing. That's what kills the most miners is smoke. And so that's the most dangerous. And so that was a really big deal, and rightly so. And that's why they basically shut the mine down. They said, how can a facility like WIPP have a fire? And that's a whole other set of issues as to how that occurred. And it comes down to being lean. Being lean so often that you just start to atrophy, right? You got to have a little fat or you will atrophy. And it resulted in the fire because they were at the minimum amount of maintenance that you could always get, right? 95% confidence level, 95% confidence level, 95, and just continue to do that. And eventually you said, well, 1 in 20, you know, that's probably I'm being mean. It wasn't that bad, but the point is that was what was found, right? Is that they were working on trying to be as economic as they possibly could everywhere, and trying to always do that, and then they end up paying the price. And so there had been somebody that actually had hypothesized that the fire contributed to the drums. And it was somebody who seemed to me to be on the border of being crazy. There was this person who had claimed that for the first months that the release, that I was convincing everybody that there was a release, and I was deluding everybody, and that it was actually the thorium from the tires that was there, and that I had hypnotized everybody to think that we actually had a release, until such a time as we took a photo of the drum that was released, and then this person changed their story to say, well, the fire just initiated the process. It triggered it. But if you look at the mine ventilation monitoring system, the fire didn't increase the variation in the underground by more than a degree or two, which is less than you get from seasonal variations, because it's so far underground. It's an infinite heat sink. And so it is possible to have a domino effect, and that had often been hypothesized, especially when it was initially believed that there was only 2 curies in the drum and 2 curies went up. And it's like, how do you get a full 2 curies out? Right? That's just kind of a very impressive, you can't design a dirty bomb to do that, get the whole 2 curies out of the drum. Maybe there was other drums that contributed, just leaked a little bit if you get enough of them. And so that was considered whether there could have been successive events or tied events. There just wasn't evidence for that. So without evidence to say that's what happened, the conclusions went based on what you could observe, what you could prove based on observation and measurement. And that was what the final assessment followed that the DOE offered, which is based on empirical observation from the instrumentation and surveys. I think that answers the question, maybe, hopefully.
Any other questions in the room? We have time for one more.
Patrick Sullivan, Virginia Tech. Thank you for the good presentation. A remark you made about midway through was that friends don't send friends dirty bombs, which is great. It sounds like the procedures going into the WIPP procedures going into this reflected a certain level of some assumptions about institutional trust. Like WIPP was trusting Los Alamos not to send them a dirty bomb. Have those assumptions changed, and is that gotten into any of the procedures?
Oh my goodness, yes. Oh, so the WIPP has just gone above and beyond in reopening. So what ended up happening is that their mission didn't change in the sense that they still had to do the regulatory compliant, safe, quality disposal of transuranic waste, but now they've got to do it in a highly contaminated mine, and on top of that, there were a whole new suite of safety requirements that were issued to them from the state and from the DOE. And so they not only had to do this new mission that they were never designed for, but they had to do it again, like in all things, with excellence. And so, to their credit, they've done that. There are issues like I showed you with the ground control. But I believe part of that is due to the fact that they were originally given an extra $100K per year to bring in all the other people and facilities to make this happen. But then that got taken away from them, and again, if you look at what is required, you need the instrumentation and you need the bodies, and those bodies have to be high quality. I mean, you've got to be rad worker, you got to be certified miner, you got to know how to operate heavy equipment, and you got to be able to do it in that environment. And you need teams of people, right? And that's not cheap. And so I believe that's what happened. I mean, I haven't spoken to the mining engineering group or mine ops or underground services in well over a year. But that would be what I would guess. Having been there, is basically they said, all right, we're going to do the best with what you're going to give us. And they've done that. And I'd say they're an extremely impressive organization, in my opinion.
Okay, Başak? And then I have one.
If WIPP was regulated by the Nuclear Regulatory Commission, would the accident have happened? And what was the role of the political pressure that the Los Alamos National Laboratory received, both from the state of New Mexico and from the Department of Energy, to clean up New Mexico from waste as soon as they could?
There are a number of questions in there. So the first one was, if NRC was regulating WIPP, would it have occurred? So NRC does regulate WIPP only for the transportation packages. They don't regulate the underground. The underground is regulated both by EPA, the state, and the DOE. And so you're saying if you swapped out DOE with the NRC, would it have still happened? Is that what you're asking?
The EPA with NRC.
The EPA with NRC. Oh, so remove the EPA and put in the NRC. So where that breach, that comedy of errors I described, that was in something that was called the National Troop Programs. And that was the oversight that was being taken place from the WIPP complex at the local site, right? And that was where managers lost their jobs. That was where the contract was yanked. That was where they swapped out the specific branches of government that were doing the oversight. And so in that sense, the powers that be agreed, in a sense, that the oversight that was taking place was clearly inadequate. In my opinion, that's how I interpret that. I'd like to take this opportunity now to tell a very funny joke about the state of New Mexico, because they told me this joke when it happened, right? It was this oxidation reaction with the kitty litter, right? And they said to me, and I thought this was hilarious, they said, it's a good thing that it was kitty litter and not dog food, because then they're just putting this bag on your doorstep, lighting it on fire and saying, put it out, WIPP, put it out. Because, that was, they were mad. I kid you not. They wanted to see blood. They were furious that this would have happened. And so when it came to the oversight, in my opinion, anybody that was committed to quality could have done the right job, right? It's just that when the managers each time, they didn't do proper conduct of ops, is what we call it. They didn't implement that, where there's a very rigorous discipline that you have to submit to. You have to buy into the. You can't, in my opinion, you can't work in our discipline unless you buy into that doctrine of conduct of ops in the nuclear industry. You have to completely endorse that, or you don't belong in the industry. You don't have the proper safety etiquette, the proper quality respect, and the proper understanding of the regulations to do your job. And so, in that sense, anybody that properly submitted to those standards could have done it. And the powers that be said, well, those that were doing the oversight didn't, right? They let that happen. And so we need people in oversight who will. And that could be the NRC. I believe it could be the EPA. I believe it could be any of those groups, as long as you have the right people there. That would be my opinion. And it's basically, what is the adherence of that person to say, I'm going to do the right thing even if it hurts, right? You might not like it. You might call me names. But it's the right way to do it. And so that's how we're going to do business. And people are going to say, well, you're getting in the way of operations, right? And you say, well, give me an exemption to the regulation and we'll do it, right? And when you submit to that discipline like that, then that kind of thing is prevented. But it requires that kind of adherence to our ethic. That would be my opinion.
Rob, you said that the WIPP is open again?
It is.
Operational, receiving waste?
It's operational again.
What did they do with that section where did they seal it off?
What did they do with? So what they did with panel 7 is, so there was a lot of very contaminated equipment. and they placed it into that panel, basically said, so we can either operate contaminated equipment or we can get new equipment, right? And which is going to be cheaper and easier and get more throughput, right? Because you're very resource limited there, right? They're back, I believe they're back on the lean machine again. And so back on the lean machine, how do you do operations where you're only given enough? That's all you're ever given is just enough. And you got to operate on just enough. And so what they did then is the contaminated equipment they would put in there, and then the idea would be that I showed you part of that process, how they do contaminated control. You can do that up until you get far enough into the contamination levels that your PPE is properly rated for those levels. And then you can't, so if you can go into a high contamination area, that's as far as you can in place. Unless you're wearing the PPE to go into a very high contamination area, basically it's like a bubble suit, right? But then you got to pay the price for your operational throughput. And so you've got to have this balance, right? What can I do? Because the requirement is, if you put someone in the mine, they have to come up clean, right? They can't have an intake, they can't have a contamination, and it's a dry, dusty place. And there are places where there's very high contamination. And how are you going to do that, right? Well, I showed you some of the picture, but the constraint on operations becomes very critical. And so it's just that balance. And so what they did is they just started putting those drums where they were allowed to put them, but you could only go back as far as it made sense based on the throughput that you could realize given those requirements that you still have to meet. So it's pretty impressive.
And then they sealed it off, that panel, after they put everything in?
They put in bulkheads on that straddled not the panel, but that room. So the rest of the panel was still available. Some had very high contamination, some had high contamination, but it left them that option to say, if we could do operations in a contamination environment and do waste and placement in a contamination environment, there's still these rooms that we can emplace in. But then they still had to maintain ground control. So you had to balance ground control with waste and placement, with your personnel, and because now, how many RCTs do you need? You need a whole bunch of them down there surveying everybody, dressing and doffing, right, and going through that process. And they're only, again, when you're on a lean budget, that drives it. But they're doing it, right? I mean, they figured it out and they did it. And I actually believed it when I left. I believed that they would, because I knew those guys. I tell you, they're crazy smart. They are. I mean, don't let the simplicity of it fool you. I think the simplicity of it speaks to the brilliance that's there.
Okay, we're unfortunately out of time, but please join us outside for some lunch and some drinks. Thank you very much, Rob. Please join me in thanking our speaker for an excellent presentation.